Now we're going to see what the difference is between barbells and bullets. Let's first define it. So a barbell is a strategy that uses a very short and a very long-term bond as a strategy, as a portfolio. And then a bullet is one that uses intermediate maturities as a strategy. If you realize like this two, like if those two are zero coupon bonds, then their average maturity is going to be the same. It's going to be 16 years. Now, the big question here is which one is better for immunization? So we're gonna see that with an example. So we're gonna use barbells, bullets for immunization. So we have a term structure here and the interest rates are given for the 2, 14, 16, 18, and 30. And then we have 5 zero coupon bonds. So we have bond A that matures in 2 years, B, 14, 18, 30, and 16. And then these are the face values of these bonds. So you should stop the video here and then you should price these bonds and then find the delta, the gamma, and the theta for all the bonds. And then we're going to define first the barbell, which is going to be equal to the bond A plus the bond D. And then we're going to define the bullet, which is going to be bond B plus bond C. And then what you want to do is you want to immunize, delta immunize E by using either the barbell or the bullet. So then you should answer the following question. Which one should you use to delta immunize the bond E? The barbell or the bullet? And then once you have done so, then given that both strategies have the same delta, but they have different gamma and different theta, then what does that mean? Is there an arbitrage opportunity? So take a time to think about this before you continue. Now, what you're gonna find is that you're gonna need to immunize your portfolio. The barbell is going to have 0.5 units of A and 0.5 units of D, and the bullet is going to have 0.5 units of B and 0.5 units of C. These are E, the barbell, and the bullet. So you achieve the immunization, the delta immunization. You see that the three portfolios have exactly the same delta, so they're delta immunized. Now, you see that the portfolios have different gamma. So the barbell has a much larger gamma, but a much lower theta. What does this mean? Well, barbell has greater convexity than the bullet, but they have the same duration. So then when interest rates go up, so let's imagine interest rates go up by 100 basis points. So then these are going to be the new values for our three portfolios. And you see that the barbell is going to have the highest value. If interest rates go down, same thing. The barbell is going to have the greatest value. So you would think, man, like this strategy, you know, there's some kind of arbitrage opportunity because if you buy the barbell, you're going to make money no matter what, no matter if interest rates go up or down. Now, there's a catch, and the catch is coming from theta, which is the passage of time. If we price our portfolio with the same rates 1 year later, what you're going to find is that in this case, the highest price is going to be achieved by the bullet and by bond E, and the barbell is going to have a lower price. So basically, the passage of time is going to be better for the bullet. Let's look at this graphically. So in here, we have our immunized portfolio. So the one with the dots is the barbell, the other one is a bullet. And let's say interest rates are at this level, 10%. So if prices go up or down, then the barbell is going to do much better. Now, what happens here with time passage? It happens that the barbell now is going to do worse if interest rates don't move. So if interest rates remain at the same 10% level, then you're going to lose money in the barbell immunization strategy. The barbell is going to be much better if there's large movements in interest rates. So that's when convexity is going to pay, when you're going to be able to make money from convexity. So if you believe that interest rates are going to remain at the same level, you should immunize with the bullet. If you believe there's going to be large changes, either positive or negative in your interest rates, then you should immunize with the barbell. Let's conclude this chapter. So we saw sensitivities of bond prices to interest rates, delta and gamma. We saw how to do portfolio immunization using delta dollar and gamma dollar immunization. We saw the definition for theta, which is the sensitivity of the bond to changes in time. And finally, we defined barbells and bullets and their advantages and disadvantages when immunizing a portfolio. So now I'm going to provide a summary of the delta gamma approximations. Like this should give you an intuition of how delta gamma approximations work graphically. So we go back to our example of the 3-year bond that pays semi-annual coupons. Coupon yield is 14% and the face value is 1,000. We already derived like the delta part. So the delta is 2818 divided by 100 and the gamma is this number divided by 10,000. So these are the value of the bond, 1094, the delta, 2815, and the gamma, 0.7919. So here we have what could happen with the term structure. So let's just imagine that the original term structure is this line here, and that interest rate, they shift up by 300 basis points. Right, so they basically go from 10%, let's say, to 13%. But now these are term structures. So if here you have one that is at 7%, so it goes from 7 to 10%. And the one here that is at 10% goes from 10% to 13%. But the point here is that all interest rates go up by 300 basis points. Now here, remember, the interest rate is in continuous compounding. So here we have our original price of the bond. So we priced our bond, let's assume, with an R on continuous compounding of 10%. Okay, and then we got this price, 1094. So this is the original price, and this is the formula to compute their bond price. This graph, what it's giving you is the relation between the continuously compounded rate and the bond price. Now let's imagine that interest rates go up to 13%. That's 300 basis points. And then the new price of the bond is going to be 1013. So that means that the real difference, and the reason I call it real, is because these two bonds were priced with the formula. Then the real change in the bond price is going to be minus $81.02. So rates go up by 300 basis points, bond goes down by $81. Now we go and we compute our delta. So our delta is the one using this formula, minus t times b from t equals 0.5 to 3. And we already did this before, and we got that delta is 28. The slope of this is minus 28.15. Now, what we're going to do is we are going to use the Taylor series expansion to approximate or to get the new bond price, but using this approximation. So it's going to be the original price, the bond original, 1094, minus the delta, 28 times 3, and the 3 comes from the 300 basis points. So we get 1010 as the new bond price. So you see that the new bond price, when you compute it with the formula, you get 1013. When you do the approximation for the new bond price, you get 1010. So now the delta approximation difference in the bond price is $84, negative 84, or minus 28 times 3. Now, what happens if interest rate now go down by 300 basis points? So then the new price, you're going to get it here, and there's going to be a real difference of $88. And now we're going to use the Taylor series expansion to see what we get. This would get you the delta approximation price in here, because this is what's along this line. So if you compute the delta approximation, you're going to get that the bond should have gone up in price by $84. So in reality, it was 88, but the delta approximation gave you 84. So you see that this line is the one that is telling you what is going on in the delta approximation. But given that the bond price has a nonlinear relation with interest rates, that's why we're going to introduce gamma. So gamma is basically going to come in, going to close the gap between the delta approximation, which is the red line, and the real price. That is going to happen in both cases. So by introducing here the gamma part, then we're going to close that gap. Let's see how that happens. So this would be the approximation with the delta plus the gamma. And let's see how well this thing does. So the delta is 28 and the gamma, which measures the convexity, is 0.79. So now you see that your bond price, according to the approximation, is going to be here. Again, is not exactly in this line, but it's much closer. So then you see that your new bond price now is going to be 1013. So the real difference is going to be, instead of $81, well, it's going to be 80.91. But you see that from these two prices, you're really close given that you're introducing your delta gamma approximation. Now let's see what happens when the price goes down to 7%. That's minus 300 basis points. So the real difference is $88. We use Taylor series approximation, and then now the delta gamma approximation says that the portfolio difference is 88.04. So you see that again, these differences are actually really close one from each other when we take into account gamma on top of delta. So this concludes this explanation, this graphical explanation of what happens graphically with the delta and the delta gamma approximations. Thanks for watching.